Okay, yeah, first of all, I'd like to thank the organizers for arranging this wonderful workshop and also for the invitation. So today I'll be talking about finiteness and classification of 61 zero supergravity. And this is based on my paper last year with Kumnum Bafar, Kai-Su at Harvard University, and also my ongoing work about the classification with Yuta Hamada at KK, and also my student, Seungmin Jeon. Okay, let's begin with the motivation. So in string theory, we know that the number of known Suzy vector in Minkowski space is finite. And on math side, there is a related conjecture by Yao. He conjectured that number of Calabi-Yau manifold in each dimension is finite. This conjecture is still an open problem, but mathematicians made big progress. So they actually proved the number of elliptic Calabi-Yau manifold in any dimension is finite. So this math proof, together with the Yao's conjecture and also unknown string theory examples, imply that string compactifications may provide only finite number of consistent quantum gravity theories. So in particular, this math proof implied that the number of 60 theories from F theory is finite. So this idea leads to the following swampland conjectures. So first, the finiteness conjecture is that the set of consistent quantum gravity theory, quantum gravity vector, is finite, and also number of massless field has an upper bound. There is a related swampland conjecture called the string Lamport principle or string universality. It claims that all consistent quantum gravity theories arise from string theory. So if this conjecture is true, then the quantum gravity landscape precisely agrees with the string landscape. As we all know, these conjectures are very bold conjectures, and at this moment, we don't know how to prove it. But at least for the theories with a large amount of supersymmetry, we can concretely test these conjectures. So for example, for the theories with the 32 supercharges, consistency together with the supersymmetry fully determine the low energy theories, which are essentially toroidal compactifications of M theory. So the two conjectures trivially satisfied in this case. 16 Suzy cases are much more complicated, but we made big progress. For example, there is a bottom-up argument on the bound on the rank of gauge algebras. So basically, the rank of gauge group for the theories with the 16 supercharges is bounded by 26 minus d for the given dimension d. So for example, in 4 dimensions, n equal for super Yang-Mills becomes inconsistent if the rank is bigger than 22. So this is quite surprising. So this finiteness provides very sharp distinction between the usual ordinary field theory and also the theories with the gravity. So for the 16 Suzy cases, so we have the finiteness conjecture. It holds. We can also use this bound to show that string Lamport principle holds in 10 dimensions with the 16 supercharges. As you all know, in 10 dimensions with the 16 supercharges, the following 4 gauge algebras are only allowed. And in particular, the first 2 gauge algebras, E8 times E8 and SO32 gauge algebras are realized in string theory. On the other hand, the latter 2 gauge algebras, including abelian factors, have no realization in string theory. And indeed, these 2 gauge algebras violate this rank bound. So therefore, they belong to the swampland. So string Lamport principle holds in 10 dimensions. In this talk, I will talk about these 2 conjectures in 6-dimensional 1,0 theories preserving 8 supercharges. So more precisely, I'll introduce a bottom-up argument to show that the finiteness of the number of massless field. Okay, so which actually provides very strong evidence for both finiteness conjecture and also string Lamport principle. And remember the math conjecture is that the number of 6F theory model is finite. So we already have some finiteness structure of a very large subset of 61 zero theories. But it's not easy to extend this idea to the generic 61 zero theories. But today I'll talk about it. And secondly, I'll present a systematic classification program for the 61 zero theories. Okay, let me give you a brief introduction to 61 zero supergravity. And in 6 dimensions, there are 4 types of massless supermultiplets. Firstly, of course, we have gravity multiplet, which contain the graviton and self-dual to form tensor field. And there are tensor multiplet each containing the anti-self-dual two-form field and real scalar field J. Here, the collection of this scalar field parameterize the moduli space known as the tensor moduli space. And there are also vector and hypermultiplets. Our claim is that these numbers are actually finite. Okay, so I'll give you how to show this. More precisely, we'll find this sharp bound. So number of tensor is bounded by 193, and this is a sharp bound, which means we have consistent quantum gravity theories saturating this bound. So therefore, we cannot further enhance this bound. So after our paper, there are two more papers discussing the bound on the number of tensor multiplet in 6 dimensions. First one is by Beaker and Seung-Ju, he's not here. And they used the geometric analysis to show that number of tensor is bounded by 567. And Hamada and Rogers, they also discussed the bound on the number of tensors using the global anomalies and SCFT classifications. So they found that number of tensor is bounded by 3003. But as you see, our bound is much stronger than their bound, and our bound is a sharp bound. So our goal is to show this bound. Shifted theories are chiral theories, so we can have gauge and gravitational anomalies. And such anomalies must be canceled to have consistent theory. And anomalies can be canceled by using 6-dimensional Green-Schwarz mechanism if the anomaly polynomial factorized in this way. So if anomaly A form is given by product of two 4 forms, then we can use Green-Schwarz mechanism to cancel such anomalies. So here, omega alpha beta is called the tensor intersection form with 1, T signature. Here, T is the number of tensors. And the coefficient here in front of R square term and also field strength square term are called anomaly vectors. Essentially, this data intersection form and anomaly vectors determine the structure of the tensor multiplets and their intersections in 6 dimensions. This factorization condition provides very strong constraint on the structure of the massless spectrum of shifted theories. For example, this combination H-3 plus 29T must be 273 to cancel the gravitational anomalies. And you can find more constraints coming from other types of anomalies. But all these constraints coming from anomalies are not enough to cut down the number of massless fields to be finite. In fact, there are some papers discovering many infinite families of anomaly-free supergravity theories. For example, in this paper by Kumar, Morrison, and Taylor, they found that the supergravity theory with this number of tensor and this E8 to the K gauge algebra becomes anomaly-free for arbitrary large K. So we have infinitely many anomaly-free supergravity theories. And you can find many more examples in these papers. So finiteness conjecture is quite highly non-trivial statement in 6 dimensions. But I will show you that even though they don't have apparent perturbative anomalies, they become inconsistent at the end. And we have only a small finite subset of consistent theories in these infinite families. Okay, let's talk about the tensor moduli space, which is a T-dimensional coset space of this form, and it's parameterized by a scalar field, which I will call J in the tensor multiplet. Then the consistency on the moduli space requires the following 3 inequalities. So first condition is to guarantee metric positivity, and second condition is to have the positive gauge coupling square for every gauge algebra. And for the last condition, we can use the consistency of the case recompactification, but you can find many more works for this last condition, including the work by Gary. And on the tensor moduli space, we have BPS object called BPS strings, and they are BPS charge source for the two-form tensor field. Then the unitarity on the moduli space for these strings requires that the tension of these strings, which is given by J.Q for the charge Q, must be non-negative everywhere in the tensor moduli space. So we have this inequality for every BPS charge Q. And these string charges must be sitting inside the unimodular charge lattice as discussed by Cyborg and Taylor. So we have this constraint for the consistency in the tensor moduli space. Okay, to analyze now, I will try to analyze the structure of the tensor moduli space, but here I will first make the following two assumptions. Our first assumption is that tensionless BPS string exists at every point on the boundary of the tensor moduli space, including asymptotic infinities. This is a reasonable assumption because in all known Schicht theories, boundaries in the tensor moduli space arise from new light degrees of freedom there associated to the Schicht SCFTs or little string theories or critical string, and they all provide tensionless BPS string at the boundary. So in all known examples, this is correct. So I believe this is a reasonable assumption. Second assumption is the classification of Schicht SCFTs and little string theories, which studied in these many papers almost 10 years ago, mostly by Jonathan here, is complete. This is our second assumption. I also believe this is a reasonable assumption because the classification scheme discussed in these papers covers all known constructions of Schicht SCFTs and little string theories, including top-down approaches such as brain construction and geometric realization, and also bottom-up gauge theory descriptions. So I'll assume these two things because we believe this is reasonable assumptions. Okay, based on that assumption, let's try to analyze the structure of the tensor moduli space and also BPS cone. BPS cone is a cone of BPS charges Q for the BPS strings, which are spanned by generators, which I call CI. So every BPS charge living inside the BPS cone can be written as a non-negative integral sum of these generators. And also the moduli vector or scalar field J must be sitting inside the BPS cone because of this J-square positivity condition. A crucial feature of this BPS generator is they are all shrinkable, which simply means that they provide tensionless strings either at finite distance boundary or infinite distance boundary, depending on their self-intersections. So for example, if C square is negative, then they give the tensionless BPS string at finite boundary in the tensor moduli space. And on the other hand, if C square is 0, then they provide the tensionless BPS string at infinite distance. This one also agrees with the emergent string conjecture by Timo.
Why are they non-negative?
Sorry?
Why non-negative?
Okay, non-negative strings we can have, but they cannot be generated. All the generators have a self-intersection negative or 0. Okay. So non-negative strings, they are some lay inside the BPS cone, but they cannot be at the boundary in the BPS cone. Yeah, every BPS charges some of these generators. And generators, their self-intersection is either negative or 0, but it doesn't mean Q square is negative or 0 because they have mutual intersection. Okay, mutual intersection can provide the positive terms when you take the square of this Q. So any BPS charge inside BPS cone, regardless of their self-intersection, whether it's negative or 0 or positive, they can be written as an integral sum of these generators having self-intersection negative or 0.
If I have BPS charge Q, can't I have an object of charge minus Q?
Charge minus Q is anti-BPS. So here we are talking about just BPS1. Thank you. Any other question? Okay, in 6 dimensions, the only BPS strings that can shrink inside the BPS cone are either the strings in the SCFTs or little strings or critical string. Therefore, they are all classified in this paper about the classification of SCFT and little string theories. So this is the all allowed BPS generators which can appear in the Schicht supergravity. They fall into the following two categories. So if the C square is negative, it corresponds to the string living inside the Schicht SCFTs embedded inside the supergravity. And if C square is 0, it corresponds to either little string or critical string, again, inside the supergravity. Since we have all classification for the BPS generators, we can extract a non-trivial structure about the tensor moduli space using this data. And essentially, BPS generators and their intersections fully determine the structure of the tensor moduli space. So if you want to understand the structure of tensor moduli space, you can just analyze the BPS generators using this table. Among BPS strings, there is a distinguished class of strings which we call H string. And this H string will play a crucial role in our discussion about the finiteness and also classification. They satisfy the following two conditions. So let's call the BPS charge for the H string as F. So whenever you see F in my discussion, it corresponds to the BPS charge for the H string. Then F scale is 0 and B0 dot F equal to 2. F scale equals 0 means the H string provides tensionless BPS string at infinite distance. And collection of these two data imply the central charge for the world CFT living on H string has 20 for the left moving sector and 6 for the right moving sector. Then from this data, you can actually understand this H string is related to the critical heterotic string. Okay? So it turns out that H strings are nothing but critical heterotic string and little string sharing the same charge class F, satisfying these conditions. In F theory or geometry, H strings are nothing but the discrete branes wrapping rational fiber curve F on the base. So for example, you can consider Hertzberg surface Fm with one-point block as a base. Then this scalar surface can be drawn in this way. Here we have a rational fiber curve with the self-intersection 0. So discrete brane wrapping this curve provides a heterotic string in the duality frame when the volume of this fiber shrinks to 0. On this side, we have another but singular fiber curve with the self-intersection 0, but this is formed by two intersecting -1 curves. Then the discrete brane wrapping this curve provides the little string. They are both H string. We are studying H string because they provide very strong constraint on the bulk shifting theory. For example, unitarity of the world CFT living on H string requires the following inequality. Let's call the gauge algebra, which intersect H string as external gauge algebra. Then the unitarity requires that total rank of this external gauge algebra is bounded by 20. Now we can prove the following three properties using the classification of BPS generators and also using the positivity on this moduli vector J. Firstly, any two distinct generators in the BPS code must intersect non-negatively. So as he asked, how can you get the string charge whose self-intersection is positive? It's because of this property. Any two distinct generators, they intersect positively or 0. Second property we can prove is the existence of H string in any 6D supergravity theory. There are two exceptions. One is T equals 0 case. It means we don't have tensor moduli space. And second exception is when B0 equals 0 case, which can occur only when T equals 9 case. So except these two cases, we can prove the existence of H string. This is a very new feature of the shifty supergravity we discovered in our paper. So now we know H string exists for generic shifty supergravity theories. So we can use the property of this H string to constrain the structure of the tensor moduli space and basically the structure of the shifty supergravity theory. And we can also prove the following containment relation. It simply states that BPS strings with charge Q, which is orthogonal to the H string, must be component of the little string theory for the H string charge class F. So we have this containment relation for every charge Q, which is orthogonal to the H string. Okay, we will use these properties to show the finiteness and also to perform the classification. Okay, these three properties actually imply that tensor multiplets and their intersections in the shifty supergravity theory roughly look like this. So basically, all the string charges belong to the following two sets. First set include the charges, which is orthogonal to H string. Then as I explained, there is a containment relation. Such generators must belong to one of the little string series of the H string. And all other generators, all other BPS charges belong to the second set, which means these charges positively intersect H string. So the tensor structure of the Shikti supergravity theory roughly look like this. And furthermore, we can prove the following. So we can prove tensors and their intersections, which are essentially specified by this tensor intersection form, and anomaly vectors can always be realized by topology of a Kähler surface such as P2 or Hertzberg surface Fn, or their blobs, which are essentially Kähler surfaces for every elliptic Calabi threefold. This is quite surprising result because this means the basis structure, tensor structure of any Shikti supergravity theory can be geometrically realizable, even though the full theory cannot be embedded in geometry or F theory. Okay? We can prove this using the properties of the H string in the following two things, but I'll skip the detailed proof. So this is basically implied that string Lamport principle is achieved at least for the tensor structure of generic Shikti 1-0 supergravity theories. Okay? Regardless of whether they have the geometric realization or not. But the tensor structure can be realized in geometry. Okay, now we are ready to prove the finiteness of the number of tensors. For this, I'll use the gravitational anomaly cancellation condition. So remember that. So some of all the gravitational anomaly contribution from every component in the supergravity theory must be 273. And here, important thing is that number of hyper and tensors, they provide positive contribution. But on the other hand, the number of vectors provide the negative contributions. There is an interesting observation by Hamada and Lodges, and they found that actually there are only some components which provide the negative contribution to the gravitational anomaly, and they are all SCFT atoms with the self-intersection -5 or below, up to -12. And these atoms, these negatively contributing atoms, support the exceptional gauge algebra such as F4, E6, and EA. And all other components in the supergravity theory provide positive contribution to this gravitational anomaly cancellation condition. This can be understood by combining gravitational anomaly cancellation condition together with the gauge anomaly cancellation condition. So here, as you see, only vector multiplex contribute to the gravitational anomaly negatively, and also this gauge anomaly cancellation condition. On the other hand, the hypermultiplex have a positive contribution. This means to have a negative contribution to the gravitational anomaly, we needed to have more vectors than hypers. So it means the self-intersection of the tensor that support the gauge algebra would be smaller. And it turns out only these SCFT atoms have negative contribution to the gravitational anomaly. And furthermore, since the number of tensors provide positive contribution to the gravitational anomaly, in order to have arbitrarily large number of tensors, we need to have arbitrarily large number of these atoms. But what I will show is that number of these atoms is finite. Therefore, number of tensor is finite. So this is the main idea, how to constrain number of tensor multiplexes. Okay, let me show you. So these atoms fall into the following two categories. First case is these atoms intersect H string positively. And secondly, this atom is orthogonal to the H string charge F. In the first case, as I explained, there is a bound on the rank of gauge algebra. And all these atoms support non-trivial exceptional gauge algebra. Therefore, their rank is bounded. It means the number of these atoms in the first class is finite. In the second case, we have containment relation. As I explained, all the orthogonal charges Q and associated BPS strings must belong to the little string theory for this H string charge F. So we have containment relation. Such atoms and generators must be element of the little string theory. It means we can use the classification of the little string theories to understand property of these atoms. And quite surprisingly, such classification of little string theories tells us that whenever we try to embed these atoms, they are always accompanied by additional methods. And once we take into account the contribution, gravitational anomaly contribution from these additional methods together with these atoms, then the total contribution eventually becomes positive. Okay? So contribution to the gravitational anomaly coming from these atoms in the second class, orthogonal to H string, eventually become positive with additional methods. Okay? We can understand this from the classifications of SCFTs and little string theories. So let me briefly introduce this classification, which was basically done by Jonada. And the classification paper tells us that SCFTs and little string theories, they are essentially generalized quibbles with the following structure of the tensor multiplet. So tensors, they intersect in like these three-shade diagrams. And this tensor structure, so tensor intersections consist of two components. One is node, the other one is a link. And node is nothing but the single tensor multiplet with the self-intersection -4, 6, 7, up to -12. And link is a finite chain of tensors with the self-intersection -1, 2, 3, and 5. And here, important fact is that if we want to increase the number of nodes, then you have to attach them through the link. So node and link, they always come together. Okay? And furthermore, if you look at these atoms, they are mostly node except this one. Okay? So whenever you want to try, so if you want to have more these atoms, then you have to actually attach them through the link. So they always come together. In particular, all the interior links are the conformal methods, which are also discussed in this paper by Jonada. And if you look at the structure of these conformal methods, for example, EA times EA conformal method, which is attached to the -12 node corresponding to one of these negatively contributing atoms, have the following tensor structure. And you can compute the gravitational anomaly contribution coming from all these extra methods, then it turns out that total gravitational anomaly contribution, whenever you have -12 node, becomes 30. Similarly, if we compute the gravitational anomaly contribution coming from node and link, their combination, roughly provides positive contribution, roughly like 30 or bigger. Okay? So if we want to embed these negatively contributing atoms to the little string theory, they belong to this second class, then eventually, with the extra methods, their contribution to the gravitational anomaly becomes positive. So this means for both cases, in the first class and both second case, the number of these atoms cannot be arbitrarily large. Okay? So this proves that number of tensor multiplet is finite. So this is our proof for the finiteness of the number of tensor multiplet in Schick supergravity series. Any question? Okay, once you have this bound on the number of tensors, you can quite easily prove that number of vectors and hypers, they are all bounded. And together, this establishes the finiteness of the number of massless field in Schick 10 supergravity series. By the way, this is a bottom-up argument covering all the cases, including the frozen phases and Yuon gauge algebras, even though I didn't explain. So this finiteness argument holds for generic Schick 10 supergravity series. Okay, let's move on to the classification. So there are some previous works on the classification of Schick 10 supergravity series. For example, Kumar, Park, and Taylor, they classified all series with the T=0 case, but containing only SUM factors. T=0 here means there is no tensor multiplet. And these series are classified by this. And also Morrison and Taylor, they classified all geometric toric bases for the F-theory model. Here, geometric toric basis means some geometric, some tensor structure coming from toric geometries. So they are classified. And more recently, Hamada and Lodges, they classify the Shikti supergravity series beyond the geometric construction, but without U1, SU2, and SU3 gauge algebras based on the anomaly cancellation and additional constraint coming from the effective field theory in 6 dimensions. So we have some works on the classification, but they are still very far from a complete classification. But now we know new features of Shikti supergravity, such as the existence of H-string satisfying these conditions, and also more constraints related to this H-string, such as the boundedness of the rank of gauge algebra, which intersect H-string and also containment relation. Furthermore, we now know number of massless field is finite. So we can combine all these new features of Shikti supergravity theory and try to suggest new classification scheme for the Shikti supergravity. As a first step, let me propose one minimal classification program. Here we put the word minimal because we'll focus on the supergravity theories that contain only non-Higgsable clusters as well as E string and M string. Here non-Higgsable clusters, which are defined by Morrison and Taylor, are basic building blocks of the construction of 6 SCFTs and little string theories, and basically they are this. So non-Higgsable cluster consists of a single tensor or 2 tensors or 3 tensor multiplets, and they all support minimal gauge algebras. Here minimal gauge algebra means some gauge algebra which cannot be Higgs because there is not enough meta multiplets. So in this program, we'll focus on the component, so these components which are non-Higgsable in the supergravity theories, and try to classify all supergravity theories containing only these non-Higgsable clusters. It's because it's much simpler, and we can set more systematic classification scheme. If we want to have a generic Shikti supergravity theories, then we actually need to unhiggs this non-Higgsable gauge algebra, basically. But here we'll focus on only these classes. In this restriction, actually, we can forget about many complications coming from U1 gauge factors because non-Higgsable clusters never support U1 gauge algebra. But once you involve U1 gauge factors, there are many complications occurs. For example, the U1 charges, the hypermultiplet charged on the U1 can have arbitrary large charges. And for example, this paper discovered an infinite family of anomaly-free supergravity theories with the U1 gauge algebra with a finite number of massless field, but arbitrary large charges. So if at this moment, we don't have very good control over the U1 gauge algebra and charged methods. But in this minimal classification program, since we are focusing on non-Higgsable clusters, we can forget about the U1 gauge algebra. So in this talk, I will not talk about the U1. As I explained, the tensor structure roughly looks like this. We have little string theories for the H string with the charge F, and all other generators and all other strings, they intersect positively with this H string. And furthermore, we know that tensors and their intersections are realizable in geometry, like the topology of P2 or Hertzberg surface Fn or their blobs. So this structure is a key property we'll use for the classification of Shikti supergravity. So our idea is very simple. Using the classification of the little string theories, we classify all allowed little string theories for the H string. And for the given classification, you can have more than one little string theories sharing the same charge class F. And for the given configuration for the tensor intersections, we attach external tensors which intersect positively to this H string to complete the theory into the supergravity. This is our basic idea. Then after that, we put the constraint from the gravitational anomaly cancellation condition. So using this idea, we can try to classify all allowed Shikti supergravity theories. And what we found is that little string theories for the H string all have p-type endpoint. Okay? which means the following. So first, we can define a projection in the tensor moduli space and the BPS cone, which we will call blow down. It's a simple projection in the BPS cone, which is orthogonal to any -1 generator. Okay, so this is the blow down. If we have -1 generator, then the intersecting curves or intersecting tensors, their self-intersection increase by 1. Okay. But this is physically very simple projection in the BPS cone. But in geometry, this blow down has very nice transitions. But so without having geometric interpretation, we can define this projection in the effective field theory. And after a series of such blow downs, the p-type endpoint or little string theories having p-type endpoint always end up with a null tensor for the heterotic string. So this property is called p-type endpoint. So if you have some collection of tensor multiplets and their intersections, if you do such projection, or if you do perform this blow down, you end up with a single tensor with the self-intersection 0 and b0.f equal 2. So all the H string or little string theories for H string satisfy this p-type endpoint condition. So the little string theories for H string is highly constrained. For example, tensor intersection form for this p-type endpoint has no loop. So you cannot have loop structure in the tensor intersection form. Furthermore, we found that all little string theories of this type are geometric. They don't have frozen singularity or Yuan gauge algebra. Okay? So you can systematically classify all allowed little string theories for the H string by using geometric classification of the little string theories for H string. So by the way, this property can be read off from the classifications of the little string theories, basically done by Jonathan and also another paper. So this is the list of all allowed little string theory bases for the H string when the number of tensor multiplet is less than or equal to 193. But before we impose constraint from for the consistent embedding of this H string inside supergravity, such as gravitational anomaly cancellation condition and other conditions which I'll explain shortly. So here we just list the number of allowed bases with respect to the number of nodes. But as you see, the number of allowed little string bases are not very big. For example, if the number of nodes is bounded by 6, then we have only 754 allowed number of bases. Okay. But here, this is before we impose the constraint coming from the gravitational coupling. We have more conditions to embed this H string or little string theory inside the supergravity. For example, the anomaly vectors B0 and Bi, they must be sitting inside unimodular charge lattice with the signature 1, T. So this is a constraint coming from the consistency of the string charges embedded inside the supergravity. And we also have gravitational anomaly cancellation conditions. So before we impose these two conditions, we have this many allowed little string bases for the H string. But once we impose these conditions, the range of possible little string theories for H string is significantly reduced. What we found is the maximum number of nodes in this LST is just 17 with this configuration. So for example, we have many tensors or many allowed tensor structure for the little string theories with the number of nodes beyond 70, but they are all inconsistent when we embed it inside the supergravity. Okay. So we have very small subset of the allowed little string bases for the H string. And it turns out that if the number of nodes is bigger than 6, actually we have only 382 allowed little string theory bases for H string. So this means little string theory configuration, so tensor structure for the little string theory, which contains a large number of tensors for H string, is highly limited. Okay. So this is a classification for the little string theories for the H string. And with this configuration, you can now attach more external tensors to complete it into the supergravity. And you can try to perform the classification of the shifted supergravity. But that part is in work in progress. With this classification data, we can actually compute the bound on the number of tensors and rank of gauge algebras. And our idea is exactly the same. We anyway classified or allow the configuration for the H string. Among them, we can try to find some configuration that can host large number of tensors and high rank of gauge algebras. And for the given such a little string theory configuration, you can attach external tensors and complete it into the supergravity theory and try to identify which configuration can support largest number of tensors and highest rank of gauge algebra. This is the basic idea. But here again, we can use the classification of these little string theories to identify configuration for the H string, which can host large number of tensors. So detailed computation is a bit involved. So let me just summarize the result. So this is the configuration for the tensors and the meta content for the maximum tensor theory. Here we have a single H string, which consists of 15 E8 conformal methods attached with two E strings here and here. And this little string theory configuration is attached to the two external tensor multiplets here and here, supporting E8 times E8 gauge algebra. So total configuration actually provides the supergravity theory. And in total, we have 193 tensor multiplets and this big gauge algebra. We found that this is the theory containing maximum number of tensors. And maximum rank theory has the following configuration. It again contains a single H string configuration with a fine E8 type tensor base supporting SO type and SP type gauge algebras. And this H string intersects a single tensor multiplet external tensor with SO32 gauge algebra. And this configuration has 9 tensors, and rank of gauge algebra is 480. And this is the maximum rank theory we can construct. So what we found is that number of tensor in shifted supergravity theory is bounded by 193. And rank of gauge algebra is bounded by 480. And this also implies that number of hypermultiplet is finite. So this is our result for the exact bound on the number of tensors and vectors. And furthermore, we found this bound, these two bounds are sharp bound, which means we have concrete quantum gravity theory saturating this bound. Indeed, these theories are realized in string theory. They are theories living on 24 instantons in E8 times E8 and SO32 heterotic strings, respectively, compactified on K3 with an E8 singularity. And these two theories are studied in these papers. So we found the bound on the number of massless fields, in particular number of tensors and rank of gauge algebras. And there are also theories saturating this bound, and we identified them. Therefore, this computation shows very strong evidence supporting the string Lamport principle. Moreover, these two maximal theories are realized in geometry. So first, the T-max theory is realized by elliptic threefold with the base given by 192 blobs of a Hertzsprung surface F12 with this such number. And maximal rank theory is realized by another elliptic threefold with this base, 8-point blob of a Hertzsprung surface F4, and it has these such numbers. And furthermore, once you do the circle compactification of this shifted theory engineered by this elliptic Calabi threefold in F theory, then it turns out that these two theories are T-dual to each other. And indeed, you can check the H numbers of these two geometries, the total space H numbers, precisely agree each other. And lastly, so this result, identifying two maximal theories with the explicit elliptic Calabi threefold, made a prediction on the very sharp bound on the H numbers of the elliptic Calabi threefold. So from this, we predict that H11 of the total threefold, if it's elliptic, then it's bounded by 491. And also H11 of the base of the elliptic threefold is bounded 100 by 194. And by the way, H21 bound in geometric models was already studied by Taylor. And furthermore, these two geometries saturate this bound, and this base bound is saturated by this Tmax theory. And these two geometries actually correspond to this very corner in the Calabi-Yau database. Okay, so this corner identified with so these two geometries. And this result predicted there would be no more elliptic threefold beyond this point. So this is our prediction. So, okay, let me summarize. So in Shikti supergravity, we proved that number of tensor multiplet and rank of gauge algebra are bounded above. And we proved this using the consistency of the tensor branch physics and also unitarity of the BPS strings, as well as the classification of Shikti SIS2025 and little string theories. And these are bound. And new structure we discovered, so for example, the existence of H string and many constraints coming from H string allow us to carry out the systematic classification of the Shikti supergravity. So we can consider the following programs. So here in this talk, I'll just introduce the minimal classification program that covers supergravity theories containing only non-Higgs subclusters. So but we need the full classification of Shikti supergravity theory. For this, we first need to understand the more constraint abelian factors, okay? Because we don't know if the supergravity theory containing the abelian factors is finite or not. And also, we made a prediction on the Hatch numbers of the Calabi-Yau threefold. So it would be great if we can prove this prediction from the purely geometric perspective. Okay, let me stop here.
Any questions? Yes.
What can you say about the representation of hypermultiplet? Yeah, it's very hard. So at least we know the number of hypermultiplet is bounded. And also for the given non-abelian gauge algebras, because of this gravitational anomaly cancellation condition, once we fix gauge algebra and number of tensors, the representation is also bounded. Okay, so if it's non-abelian. But problem is representation for the abelian gauge algebra. In this case, there is no bound at this moment, no concrete bound at this moment, which charge we can have in the supergravity theory. So once you have the charge bound for the abelian factors, yeah, probably we can easily prove the number of allowed low energy effective field theory in SIS2025 theory is finite. So we should first attack how to bound the abelian charges. Yeah, but non-abelian ones, they are already bounded by the anomaly cancellation. Thank you.
Thanks for the nice talk. So how many, do you have a sense of how many SCFT sectors can be in a given supergravity theory, which would be kind of decoupled from one another, or?
So you are asking how many SCFTs we can obtain from the gravitational theory once you decouple the gravity?
Yeah, so for example, if I just gave you a bunch of independent -2 curves, I would count those as independent SCFT sectors once I decouple gravity. So there's a finite number. How many are there? Or, do you know? Or?
Yeah, actually we have finite number, yes, but it's very big. So if we are just talking about the SCFTs, so before we impose the constraints coming from supergravity, such as the gravitational anomaly cancellation and so on, what we found is the number of available 6 SCFTs is order of 100,000. Yeah. But once we impose the gravitational anomaly cancellation condition together with the embedding inside the self-dual lattice, the number is highly reduced, but I don't know exact number, but the maximum order is about 100,000.
Okay, thank you.
Any other questions? Okay, if not, let's thank Hee-Cheol again.